Today we're going to talk about misconceptions about gravity. Believe it or not, there are some very interesting misconceptions because some of them are just outright ridiculous and others are actually quite hard to understand. So I'm just going to go through a few, maybe like 7 examples about these common misconceptions. So, most of these have to do with astronauts in space. So let's take a look at this. Misconception number 1. Astronauts on the space station do not weigh anything. That's misconception number 1. Now, this is one of those that it's kind of, well, that makes a little bit of sense there, because we always hear on the TV shows that astronauts are weightless. Wow, I would love to go to space because then I would weigh a whole lot less. But that is not the case. Astronauts do have weight, as you've seen from the universal gravitation constant, the universal gravitation law. F of g is equal to g m1 n2 over r squared. So the astronaut and the Earth both have a mass, and the distance between them is very large. So f of g is going to be quite small. So even though it's really small, there is a limit to how small we can do. For example, 1 over 10 raised to the power of infinity is considered 0. Is pretty much considered 0 because it's too small for us to even conceptualize. So that is equal to 0. However, in this case, we have a number who's not nearly as small as that. It's very small, believe me. But here's the thing. If astronauts, or when this is the Earth, the astronauts have a weight because there is an attraction between the astronauts and the space station. If this is the space station right here, orbiting around, there's its little rocket booster and everything. This is the space station. The space station is orbiting around the Earth. It's going all the way around the Earth. If it did not have gravity, there was no attraction between the space station and the Earth, then there would be no, and then the space station might just float off. So by that sense, the astronauts inside the space station must also have a weight. So that's just one way of looking at it. Okay, let's move on to misconception number 2. So, misconception 2. There is no gravity on in a vacuum. I do not think I spelled vacuum right. Let me try. Nope, it's 2 U's. Okay. There's no gravity in a vacuum. Now, believe it or not, there's a large misconception that the air pushing down on us is what holds us to the floor. So this is the air. There's a misconception that the air pushing down on us is what holds us to the floor, not the fact that there's gravity, but that the air is pushing down on us, which is causing us to stay on the floor. So in a vacuum, for example, so if we took a chamber and we had a guy, and he was in a spacesuit. He's in a spacesuit. They would believe that if the air is zero, that if there is no air, that he would just be able to float around, go wherever he wants, kind of do whatever. And it's very interesting. For a long time, there was a theory that they could create an amusement park ride in which people put on little spacesuits. So they would just have you put on a spacesuit, put you in a chamber, evacuate all the air, and you just be able to float around there for maybe 30 seconds to a minute, and you just zero gravity. But unfortunately, it is not the air. So that is why that is wrong, because the whole idea that it's not the air pushing down on you, it's gravity. Misconception number 3. Orbiting astronauts are not accelerating. This one is quite interesting because it may seem kind of hard to grasp unless you know the concept of acceleration very well. We know that acceleration is a change in velocity. Let's expand that out. Velocity. So, acceleration is a change in velocity. So, remember that velocity is a vector. So it has magnitude and direction. So, when you have a magnitude and a direction, if either one of these changes, it's considered an acceleration. So, what happens when astronauts are orbiting? Well, they're right here. So if the astronaut's orbiting, then they're moving along the outside. But what's keeping them in orbit? Or how are they orbiting? They're going around the Earth. They're basically falling towards the Earth, like this. They're falling in a parabolic trajectory. Their intent is to go like this, from here, and then this is the surface of the Earth. But there's one problem. The Earth is curved. But they're so high that when they start to fall, just as they're about to hit the Earth starts to curve away. So they're basically in a continuous fall. So that's how they're entering orbit. However, they're also changing direction throughout this whole time that they're in orbit. So, since they're changing direction, they're changing velocity, which changes acceleration, so they are accelerating in space. If Earth was not spinning, let's take a look at the fourth one, which I think is going to be the last one we're going to do today. Fourth one. If the Earth, we'll probably do one more. But if the Earth was not spinning, there would not be enough gravity to keep us on the Earth. So this is a common misconception here that that the Earth spins at a very high rate, and if it stopped spinning for whatever reason, we just float off the Earth. But here's why that's not correct. When the Earth spins, it creates some force called centrifugal force, which is actually kind of the force, when you're in a variation of like the teacup ride at Disneyland. You feel like you're being pressed against the side. That's generating centrifugal force. So if the Earth was not spinning, there would actually be more than enough, because centrifugal force is actually forcing you to the outside. That's actually part of the reason why we get the bulge around the equator. Why, when I've been drawing the Earth as a circle, the Earth really looks something like that. No, it looks something like that. Just a little bit bulky around the middle. That's what Earth should look like. However, just for the ease, I've drawn it like this. But as you can see, centrifugal force is actually counteracting gravity. So that is why, if you have gravity, that if the Earth was not spinning, there would still be gravity. Now, the last one is the granddaddy of all of these misconceptions here. It's very, very common and very, very easily missed. It's very tricky. Gravitational depends on the mass. So gravitational acceleration of a free-falling object depends on its mass. Now, this one is very easily missed because of a couple of reasons. Remember the universal gravity equation, G m1 m2 over r squared. Well, they say to me, look, there's masses here. Mass 1 is obviously the mass of the body. The mass 2 is the acceleration that the object is accelerating towards. So therefore, f of g is equal to m1 m2 over r squared. So g m1 m2 over r squared. Therefore, acceleration has to depend on the mass. So, but let's take a look at how this is what's actually happening here. So we know that F is equal to ma. So that means we know that so we know that F is equal to ma. That's what Newton said is second law. So now if we substitute this F for this F, we get ma is equal to g m1. Okay, that looks a bit like a 6. Let's try that again. Okay, so g m1 m2 divided by a, or divided by r squared. So here's what's interesting. If we take a look at this, we saw for A, this mass and this mass will cancel out because they're going to represent the mass of the same body. So then what we're left with is A is equal to g m2 over r squared. So what you don't see here is you do not see in here, what you're not seeing is the mass 1. Now mass 2 is going to represent the mass of the Earth. So the key part here depends on its mass. So because it doesn't say depends on its mass, that's why this statement is false. If it says gravitational acceleration depends on the Earth's mass, then you can make an argument that that is true. However, because it depends on its mass, then that's the reason why it's not fair. So these are the most common misconceptions. I find that these are usually the ones that physics teachers put on tests, quizzes, or just very difficult homework assignments.